Hello, welcome to the third lecture on network theory. Okay, in the last two lectures what we did was we just went through some basics of network theory, like what are the elements involved, which of them are sources, which of them are sinks, then some basic definitions regarding resistance, capacitance, then Ohm's law, we went through Ohm's law, and we also considered in a little bit detail what the concept of voltage, current, and impedance is, right? In this lecture, we'll start with some basic concepts. We'll just continue with the basics, but this won't be just some theory stuff. Okay. So now in this we will start with the concept of series and parallel connection. Connection means connection of what? Of elements, right? Series and parallel connection of elements. So we'll just understand the concept using some resistors, inductors, and capacitors. Okay. First of all, let's have a look at series connection. Okay. So what is a series connection, or how do you say, or when do you say when two elements are connected in a series connection or not? That is the question. The idea is that for a series connection, the current flowing through the elements will be same. Okay. Now let's draw some elements and see. So let's consider the example, this one. We have two resistors, R1 and R2, right? And if a current I is flowing through R1, obviously it will have to flow through R2, right? Because there is no other way, or there is no other branch to take some current away or give in some current. So if we write I1 as the current through R1 and I2 as the current through R2, here I1 will be equal to R2. So this is the condition. The current through one element should be equal to the current through another element. Suppose if we had another resistor here, say R3, then the current through this one will be the same as these two. So then that would have been also, that too would have been in what do you say, a series connection with these two. Right. So now let's so this whole thing, right? Let me just remove this. Okay. This whole thing, this will have an equivalent resistance R. Suppose that is, we are connecting two resistors, each having separate resistance, and we want to find the equivalent resistance across X and Y. That is, if we are giving some voltage across X and Y, then some current will flow depending on the resistance, right? That is the idea. So we want to find the equivalent resistance across X and Y. Here R1 and R2 are connected in series. Then equivalent resistance will be R1 plus R2. Okay. And suppose here instead of resistance we are using two inductors, right? Using two inductors, each having an inductance L1 and an inductance L2, and we want to find the net resistance R. sorry, net inductance, my mistake, L. Then what will L be? L will be L1 plus L2. Actually, we can derive, we can come to this values, this relations, this R equal to R1 plus R2 and L equal to L1 plus L2 using Ohm's law and the relationship between voltage and current, but we are not going through that. I am just assuming that you will understand this, and I am just taking that for granted. Okay. Then which is the third passive element that we had considered? The capacitance, right? C1, C2, X, Y, C. C will be equal to, what will C be equal to? C won't be equal to C1 plus C2. No, it will be 1 by C1 plus 1 by C2. Right. C will be 1 by C1 plus 1 by C2. When we come to the parallel connection, this will be similar in the sense that there the way inductance and resistances react, it will be similar, and the way capacitance react, it will be somewhat different, right? So parallel connection. Okay. So again, when do we say when two elements are in parallel connection? When the voltage across the elements are the same. Okay, let's right away dive in. Okay, sorry. Again, R1, R2, right? So here, like you can see, here the elements were sort of connected one after the other, right? But here the thing is that both the terminals of the elements are coming in contact at same points, right? That you can understand from the image. So here what it means is that the voltage across R1, which is equal to V1, and the voltage across R2, which is equal to V2, they will be the same, and assume some current is passing through here, right? And the net resistance R will be, what will R be? R will be 1 by R1 plus 1 by R2. This is how two capacitors behaved in a series connection, right? And if we draw for let's say two inductors, L1, L2, again the voltage will be same, V volt, then the net inductance L equal to 1 by L1 plus 1 by L2. Then I think you can assume what happens or how two capacitors will be behaving. How two capacitors C1, C2, how will it be behaving? C will be equal to C1 plus C2. Again, we can derive these equations from basic Ohm's law and all, but just understand this is how inductors, capacitors and resistances behave when they are connected in series and parallel. Okay, let's just go back just to make sure. So when two resistors are connected in series, and not a series connection, current flowing through the elements will be the same. When two resistances are connected in series, they add up, resistances add up. When two inductors are connected in series, they add up. When two capacitors are connected in series, they don't directly add up, but what adds up is the inverse of the let's say impedance. Okay, what adds up is inverse of the impedance. Again, here in parallel connection, what is a parallel connection? It is a connection in which the voltage across the elements are the same. So here, when two resistors are connected, they don't just add up. When two resistances are connected in parallel, they don't just add up. What happens? There again, the inverses add up, right? The same thing happens for inductors, but for capacitors, the opposite happens. The capacitance just adds up, right? So to make sense of this, we'll have to go through, not make sense of it, to complete this understanding, we have to go through this concept of what is called as a conductance, G. Okay. So the conductance is defined as simply as the inverse of resistance. So G equal to 1 by R. That means G equal to 1 by V by I, equal to I by V, right? G equal to I by V. So what happens when two elements, okay, having conductance G1 and conductance G2? So what does it mean when I say this element? This is the circuit symbol for a resistance or a resistor. So what does it mean when I say that, okay, this is having a conductance G1? It means that it has a resistance 1 by G1. Again, this has a conductance G2. It means it has a resistance 1 by G2. Okay, what happens? What is the equivalent conductance? G equal to 1 by G1 plus 1 by G2. What happens in parallel connection? G1, G2, G equal to G1 plus G2. Okay. So why is this happening? In a series connection, the conductance don't add up directly, right? Conductance effectively reduces, right? But resistance, if we go back, in a series connection, resistance increases, resistance, and the same thing inductance. But in a parallel connection, resistance and increases, reduces. Similarly, in a series connection, conductance decreases. In a parallel connection, conductance increases. So to understand this, we have to, this is sort of logical in the sense that it directly follows from the definition of resistance and conductance, right? So what is resistance? What is resistance? Resistance, of course, it is a property of the material, but what is resistance? It is the resistance offered to the current, right? It is resistance offered to the flow of current. So what are we doing if we are placing, let's take a new page. So what is resistance? resistance is something that is opposing the flow of current. So, when you are keeping something after the other which opposes the flow of current, that means more of that is coming, right. Like suppose some water is flowing and you build a wall, right. You build a wall, that means it is offering some resistance to the flow. So, if series resistance is something like you are building another wall over the previous one, that means the resistance to the flow of the water is increasing, something like that, a simple analogy, do not take it literally. Okay. Anyway, that is the idea. Resistance is the opposition to the flow of current. It means that is why, right, that is why here in series connection, when we are connecting one resistance after the other, when the current is coming here, okay, it has to face some resistance, some opposition, and again when it reaches here, it has to again face some opposition to get to this point, right. So, effectively the resistance or the opposition to the flow of current is increasing, that is why series connection increases resistance. But when it comes to parallel connection, what happens, the current reaches here, okay. So, at this point the current only has one path to follow, it definitely has to go through this, and that has an increased resistance. But at this point the current can flow through here and it can flow through here. So, depending on the resistance of each path and the voltage given, some current will flow through here and some current will flow through here. That means even though there is resistance offered to each branch, since the current can go through, okay, some will go through here and some will go through here. So, the current does not get that much opposition as if it would have been in the series case. That is why here resistance, net resistance is increasing, right. The same argument goes for inductance and capacitors, but in their respective ways. So, that is the concept of resistance. And conductance means what? Conductance is it is the ability to conduct electricity, or simply said, how much current or with how much ease the current will flow through, that is the sense of conductance. So, whatever argument we made for series and parallel connection of resistance, you can use the opposite argument for conductance, because they are inverses. Okay. Okay, now let us see some simple network resistance problems. Okay. So, question: these small dots, these are just to show that they are terminals, they do not have any other meaning, do not get confused with that. Okay. So, I am naming this terminal as A, this one as B. So, this one will be X and this one will be Y. So, this is a 1 ohm, 4 ohm, 3 ohm, 2 ohm, 2 ohm, 6 ohm and 7 ohm. So, using this concept of series and parallel resistance that we have seen, let us find out the net resistance across R AB, R XY, R AX, R BY. Okay, so we have to find all these. So R AB, right? So when we are considering R AB, right, R AB. So for RAB means we are giving a supply across RAB and we are finding the current voltage to current ratio. That is the idea. So when we are applying this current to A and across A and B, what happens? Current will flow like this. Okay. At this point, how will the current split? It will go through here. It will go through here. Will it go through here? No, it won't. It won't pass through this branch. Why? Because it is an open end. Current always needs to go back to its original point, right? So here it is what is called as an open circuit. Current cannot jump from this point to this point. So whenever the current reaches here, it cannot flow through. So current won't flow through this point. So current will come here. It will come here. Again at this point, it will go here, but it won't go this way because of the same reason. And at this point what happens? Anyway, current is coming here, current is coming here, they both join and it will pass through here. This is how the network works. So to find RAB, let's write like this. The equivalent resistance circuit network is, it is like this, right? 1, 4, 3, 2 and 2, A, B. Okay. So now from this, what can you identify? Which all can you identify? Here 4 and 2 are in series, right? And this this equivalent resistance of 4 and 2, it is in parallel with 3. It is in parallel with 3, and this whole thing, it is in series with 2 and 1. So RAB equal to 4 in series with 2. Okay, this is in parallel with 3. Please observe the notation. When you just put a plus, okay, it is a series. 4 is series in 2. It is with the whole thing is parallel with 3, and this whole thing is in series with 1 and 2. Okay. So 4 plus 2 is 6. 6 parallel 3 is 2. You can do the math. 4 plus 2 is 6. 6 parallel 3 is 2. Plus 1 is 3. Plus 2 is 5. Okay, so that is the answer. So now let's see XY, right? XY. So again we have to use the argument that we used earlier for RAB. We have to see if we give supply here, in which all ways will the current pass. So if we give supply here, the current will go here. It won't go through this path or this path because they are open circuits. So it will go through here. It will flow this way. It will flow this way, and here it will come and join and go like that. So for RXY, the equivalent resistance, equivalent circuit is X, Y, 6, 4, 7, 2 and 3. Okay. So now here what is happening? 2 and what do you say? 3 are in series. Okay, 2 and 3 are in series, and this combination is in parallel with 4 and that combination is in series with 6 and 7. Okay. So, how do you write? 3 plus 2 is in parallel with 4, is in series with 6 and 7. You can do the math, it will come to something like, I think 137 by 9. Okay. Now let's see which one. R okay, R by, R by, so small letter b here, R by. So when we connect supply across R B and Y, it means there won't be any flow through this branch and there won't be any flow through this branch. So the equivalent circuit will be so we have a 4 here, 3 here, 7 here, 2 here, 2 here, B and Y, right. So how will this work? How will this work? So here you can imagine, even in this one you can imagine, like you can just take this arm and put it here, take this arm and put it outside, so it will be more easy to visualize. Similarly, you can take this arm and put it outside. So what will happen? This 4 will be in parallel with what? This 4 will be in parallel with the what? Combination of 3 and 2, right? No. Here 3 and 4 forms a series connection. Earlier in these two cases 3 and 4 didn't form a series connection, but here 3 and 4 forms a series connection, right? That series connection is in parallel with 2, then the whole thing is in series with 2 and 7. So when you write this, it will be what? 3 is series with 4, which is in parallel with 2, which is in series with 2 and 7, right. So it will come something like 95 by 9, I think. Okay. Sorry, that is this is B Y. This will be AX. So AX, what will be the case? Again, this won't be there, this won't be there, right. This path won't be there, this path won't be there. So if you draw for AX, okay, A, okay. So this is AX. So what happens here, when the current comes here, the current can go this way or this way, but the thing is that this is a closed loop, right, and it won't, current won't flow and come like this and go like this or anything. This whole thing, okay, let me redraw this 1 6 AX, this whole thing can be drawn something like 4 2 3, something like this. So when the current comes here, it won't go through here because there is no potential difference between these 2 points to flow through there. So it will just go through here. So this is just 1 plus 6 equal to 7. Okay. This is for R AX. So I am stopping the lecture here. In the next lecture, we will continue with the couple of problems and move forward. Okay, let's before winding up, let's start. What did we see? We started with the concept of series and parallel connection. We defined series connection as the connection through which, in which the current through the elements are the same. Okay, and equivalent resistances and things like that. And parallel connection as a connection in which the voltage across the elements are the same. Okay. So from this you could understand that resistances and inductances react in a similar way, but capacitances react in a different way. And we introduced the concept of conductance, which is an inverse of resistance. And for inductance and capacitance, there is this concept of an admittance. We will come to that when we go to the AC steady state problems. Okay. Then we started to solve this problem. So in the next lecture, we will go through a couple of problems and then we will move along with other concepts.